Okay, so first of all, I would like to thank the organizers for having me here. It's my first time at l'École Normale Supérieure in Paris. And I'm very happy to talk with you about gravitational waves. You are very welcome to ask questions during the talk, so that also I can, gauge more how well I'm doing in trying to explain things. So let's start. So I want to start with this picture, which maybe some of you have seen. Is the collection of all the black holes and neutron stars that LIGO and Virgo have detected so far, that have been published in papers. The y-axis here is the mass in solar masses of the objects. The blue are the black holes, and here is the very first event 10 years ago in September, the 14th of September 2015. What you see here is basically represented one black hole that merged with another black hole and form the final black hole here. This is the first binary neutron star detected, the 17th of August 2017. The neutron star in this stellar graveyard represented with the orange dots, and here is the event. And by the way, this is a picture of a numerical relativity simulation showing the two neutron stars very close to merging with each other. This is the largest binary black hole observed so far. The masses are the largest one, 100 solar masses, and forming a final black hole around 150 solar masses. Another examples, the largest asymmetric system with a mass ratio around 10 that was discovered the 14th of August 2019. I will come back to these events later. And I want also to emphasize that besides these almost 100 events observed in the first 3 observing run, the LIGO, Virgo, and Kaga collaboration are going through a new run that started 2 years ago and is called O4, and until now has announced 203 candidate signals or signal candidates. I cannot talk about these events because the papers we are writing papers. But I will also discuss later one event that was actually published last April of last year, which corresponds to a neutron star black hole system, so a mixed binary, discovered the 29th of May 2023. Now, the red dots that you see still in this plot are the black holes that we see in our galaxy in X-ray binaries. So they have a companion, which is not another black hole or neutron star, it's a star. And we see this object as X-ray. And finally, the yellow dots are the pulsars that we see in our galaxies. These are neutron stars. We see many of them. And this plot puts together everything, including the distribution in masses, new masses that we are seeing with the black holes. So in this talk, I will describe the theoretical frameworks that have underpinned these observations. I will describe what role the waveform models have played in detecting the signals, and also in interpreting them, which sources are emitting these systems. And I will also provide some highlights in astrophysics and fundamental physics of the results. And then I will describe the theoretical challenges which needs to be addressed for future observation. The detectors are becoming more and more sensitive, and also there will be new facilities on the ground, and certainly a new detector in space, which is called LISA, which are going to do measurement with much higher precision, and so we need actually to improve our theoretical predictions. So let me start just by some basic things. So the gravitational waves were predicted by Albert Einstein in 2 papers, one in 1916, the first one, where he linearized the Einstein equation that I wrote here in full glory. R mu nu and R are describe the curvature of spacetime. They depend non-linearly on the metric G mu nu and its derivatives. T mu nu here is the energy momentum tensor. And Einstein linearized these equations with respect to a Minkowski flat spacetime, small perturbation h mu nu, And in a particular gauge, he arrived to this equation here, which you can see the analogy with electromagnetism, where h bar mu nu will be a mu, the electromagnetic field, and t mu nu you would replace with the current. The box here is just the D'Alembert operator. Einstein made a mistake in the first paper. He didn't get right the degrees of freedom of the gravitational waves, but he corrected that in a subsequent paper in 1918, where for the first time he derives in the correct form, although there is a factor 2 wrong in the formula, the energy flux, how much energy in gravitational wave is emitted, and its dependence on the multiple moments of the source. And the first multiple moment that appears is the quadrupole. For this reason, the gravitational wave sources can be emitted by kind of rotating dumbbells like a binary of 2 stars. Of course, at the time, Einstein did not think about a binary star, because at the time, people didn't know that this binary even existed. But of course, this has been realized later on. Now, I wanted also to introduce 2 other important papers that are playing also an important role in gravitational waves observations, are the solution of a black hole, non-rotating and rotating. The first one in 1916 by Schwarzschild, Karl Schwarzschild, and the second paper many years later in 1964 by Roy Kerr. And as you will see also later, until now, both the observation of gravitational waves and other observations that today we have, including the one of the black hole at the center of our galaxy, are showing that the solution of black holes in general relativity are still valid. They are not violated. Now, for our particular problem, we are interested not in isolated black holes, but as I was saying, in a black hole in a binary. So this little picture here represents the black hole as funnels going around each other. One is very big, the other one is very large. And as you will see later, we have gained a lot of information starting just from this solution of isolated black holes. You can actually build information, you can gain information on the two-body problem, starting from the one-body one, using some mapping that depends on the mass ratio of the binary. Okay, so now let me give a little bit more information about the strengths of the gravitational waves. And I'm using some basic gravity, like Newtonian gravity, for example. So if you have a binary system, you can introduce the total mass of the system, the velocity in the binary, the reduced mass, and the so-called symmetric mass ratio, which is the reduced mass divided by the total mass. And the nu goes between 1/4 when the two bodies have equal mass, and 0 when one body is much larger than the other. So what we learned from the paper of Einstein is that the strain, or it's a tensor actually, has indices there, but I removed the indices just for simplicity, is a dimensionless quantity. It depends on the variation in time, the second derivative in time of the quadrupole. D is the distance to the source. And now if you have a binary where the two objects move on a circular orbit, you can actually write at leading order that the quadrupole, the second derivative of the quadrupole, can be written in terms of the relative velocity, like v over c to the power 2. And there is this dependence on the mass of the binary, the Newton constant, the speed of light. Now, if you take a neutron star, in a Virgo, put it in a binary neutron star in the Virgo cluster, and you compute this formula here, almost at the end, when the two bodies are close to merger, and v is almost the speed of light, you get a very small number, 10 to the minus 21. Now, of course, if you put the binary in our galaxy, this number will be much larger. The Virgo cluster is around 20 megaparsec from us. It's the cluster, closer cluster which has of the order of 3,000 galaxies. But the problem is that if you put the binary in our galaxy, you will not find that this binary in a time scale of our life, even the life of the Earth, is going to merge. It's very rare that binary of neutron star and black holes merge with each other. There are many binaries, but they are a very large separation. And it takes millions or billions of years to come close to each other and merge. So that's why we have actually to build detectors that are sensitive to a very large volume that contain many galaxies, and then the possibility that we have a merger is very high. Today, I will show you the current detectors can detect a signal every 3 days. Now, if you compute the luminosity, which is the energy per second, just taking the derivative of h and then squaring it, similar to what you would do in electromagnetism, you get this formula here, where the dependence on the relative velocity on the speed of light is to the power 10. So this also tells you that in order to have a very large energy flux of power, you need to bring this object at very high speed. And you can do it only if the objects are compact, like black holes and neutron stars. If you have two normal stars, like our sun, you will not be able to bring them at very high velocity because they are going just to be disrupted. Okay? Now, this energy is very large. It's emitted in particular at the very end when the relative velocity becomes, as I said, of the order of the speed of light. And another important information is that once the waves are produced somewhere, they travel through the universe to the Earth, and they are not much affected by whatever they encounter. So if you can actually reconstruct the waveform, you have a lot of information about the source that has emitted that. But I will show you at the end that actually with more sensitive detectors that we will have in the future, we have to start worrying about these kind of effects, like the one that is called gravitational lensing, that we have also in electromagnetic astronomy. Okay, so we detect these systems, these sources, with interferometers. And this is just a scheme of one of the interferometers. We have 2 LIGO detectors in the US, Virgo, which is a French-Italian-Dutch collaboration, a detector in Japan, which is called Kagra. This is the noise spectral density of the detector, sensitive between 20 Hertz and a few kilohertz. And the way in which we detect gravitational waves is the fact that if you have a gravitational wave that impinges on the screen of this slide, the mirrors, the proper distance between the mirrors is changed, like in this little animation here, this ring here. And so what is measured is the differential mode of motion of the mirrors with laser light. And so normally the interferometer is in a configuration for which there is a dark part here, no light goes out. But when the gravitational wave arrives, because of this movement, the variation in the distance, you have some light that leaks out from the dark port and go to the photodetector. Now, the displacement in the variation in the distance is proportional to the strain that I was mentioning before through the length of the Fabry-Perot cavity. And so if you want to measure that 10 to the minus 21, you need to do measurement of the level of 10 to the minus 16 centimeter, which is really fantastic, and we can do it. So this is the way in which the waves are detected, but for our talk today, I want also to introduce another fact which is quite important. So in the case of gravitational wave from binary systems, we have a luxury that we can predict in advance the signal by solving the Einstein equations for 2 black holes or neutron stars going around each other. And so we use signal processing or match filtering. And I have a little animation to show you how it works. So in the bottom panel, you have the data in black, which contain noise plus a signal. You slide or correlate a template in pink, and you maximize on the parameters of the binary, the masses, the spin of the black holes. And when that correlation becomes larger than a certain threshold, which you have set depending on the knowledge of the noise in the detectors, then you can claim a detection. Now, for that, we need to build template banks. And the template banks contain many templates, 100,000 of them. We need to produce even million templates when we do follow-up analysis using Bayesian methods. And so you understand that this problem is complicated because you have to produce waveforms that are very accurate, and you have to be also very fast. Now, let me go back to the slide I was having before, but now I'm adding another piece of information. Before, I was just talking about the amplitude of the strain of the waveform. But because we use match filtering, what is important is to keep track of the phase, of how the wave oscillate and how the phase changes over time. So what is this phase? So if you use the quadrupole formula, the dependence on the orbital phase, so you have the binary, they move like on a circular orbit, for example. You have the orbital phase. Because of the quadrupole formula, there is a factor 2 here. If the emission was due to a dipole radiation, then you would have just 1 instead of 2. Okay, that's where the 2 comes from. But how do we get this phase? So now I give you, a basic information how we do that. Of course, it's also more complicated, but let me say the basic things. So on one side, we know that we can compute the binding energy of the system, which I wrote here at leading order in an expansion in V over C. So the leading order term is just the Newtonian binding energy. Just using the viral theorem, you just write it in this form. Mu is the reduced mass, right? On the other hand, we have the gravitational wave luminosity, how much energy is emitted at infinity. And this is the formula that actually comes from the paper of Einstein with the correction of the factor 2 if you apply it to a binary system. Now we use the energy balance equation that says, okay, the variation of the binding energy of the system has to be equal to minus the flux at infinity. And in the case of a binary moving on a quasi-circular orbit, everything depends on omega, which is just the orbital frequency. So you can rewrite this equation like d over the omega over dt. So at the end, you get omega dot, then you integrate twice, and you get basically the phase. So this is just to say that there are 2 important ingredients here, at least for the in-spiral. You have to know very well the binding energy, and you have to know very well the emission of gravitational waves. Of course, you cannot just use the leading order terms here. You will get something that is not correct. And you have to add corrections, as we will see in a moment. Okay? If you have any question, please ask. I will be very happy. Yes?
So in your mass filtering slide, you discussed the mirrors. They are stretching and squeezing. The ring of particles you have, it has to be a freely floating scenario, the ring of particles which stretch and squeeze. So the LIGO mirrors, are they close to being in the state of freely floating or something?
So the mirrors are hung by wires. So they, above a pendulum frequency of a few hertz, they are actually free of moving. But it's only above, a few hertz. Of course, we have a lot of noise also, like seismic noise. There are many noise that we have to take into account. In fact, the noise spectral density I was showing you is the addition of all this noise, okay? But the pendula are actually free of moving above the pendular frequency. And so you consider them as freely moving. Okay? Okay, yes?
Regarding the phase as a function of time, what is known about the possible fluctuations of the omega of tau prime or t prime, which will kind of induce some kind of...
So, sorry, you're asking about the phase? Which fluctuations?
When you have the phase, like this is the integral of the pulsation. Yeah, and so this pulsation...
Sorry. Yeah, please say, because I don't hear you very well.
Is it fluctuating as a function of time, or what is known about the, like which would kind of blur? I mean, is the phase like the gravitational wave, or is this something which I can assume that is going to give a very stable frequency?
I mean, this omega dot here the frequency can change. It's increasing over time, right? Because, in fact, this is what I was going to say in this formula here. Because the binary is merging, it's going toward merger, R is decreasing, so omega is increasing. But omega can have oscillations. For example, if you have eccentricity in the binary, then omega will have oscillations. If you have the precession of the spins of the 2 black holes that precess along the direction of the total angular momentum, also this frequency is going to oscillate. But that doesn't matter, I mean, in the sense, you will take into account all these effects.
Okay, but there are no fluctuations which would blur essentially.
But fluctuation due to the noise of the instrument, or what?
Not like
Well, I mean, you are really dominated just by gravitational interaction here of the two bodies going around each other. Now, maybe what you are thinking is that suppose that the black hole are surrounded by some accretion disk, are in an accretion disk. Yeah, I have a slide about that. This effect could actually, for example, if you are in an accretion disk, you can have a torque that is applied, you know, on this, and you have to take into account that. But these are, at the moment, these are very small effects, but we have to take into account them in the future because we will have a much better sensitivity. So at the moment, this is not a problem. Also, for stellar object black hole, for which I mean a black hole that have a mass between, let's say, 5 and 60, 70 solar masses, the binary of these objects, at least for what astrophysicists say, they close to merger, they are not supposed to have a gas around. If they had gas around originally, the gas would have gone away during all the time, you know, the binary existed. But sometimes this binary can be in an accretion disk. That's true. But this is a very small subpopulation for the event we are seeing. Okay, but that was a very nice question. Okay, the video already finished. Sorry, this was a video representing 5 black holes at the top and a binary neutron star in the bottom. I wanted just to reflect on the length. So why the black holes are so short and the binary neutron star is so long? Well, the spiral ends at some point. Now the two objects plunge with each other. And you can, roughly, this is not very precise, associate a merger frequency to this number, 4,400 Hertz, divided by the total mass of the binary in unit of the mass of the sun. So a neutron star has a mass between 1 and 2 solar masses. So this means it's going to merge in the kilohertz. The detector bandwidth starts around 20 Hertz. So you have even a few minutes, right? It's very long. In fact, this event lasted for 3,000 cycles in band, for a minute. The black holes have a larger mass, and so they merge at lower frequency, and so in the middle of the bandwidth of the detector, and so the signal is going to be shorter. But this formula also tells you that if you continue to increase the mass of the black hole, at some point they are going to merge outside the bandwidth. And in fact, a million solar mass black holes, which are the sources for the detector in space, as we will see, they merge in the millihertz. We cannot detect these sources on the ground. We have to go in space because we are limited by the seismic noise. We cannot go below 1 hertz, more or less. So another reason to care about the waveform shape and the predictions of the waveform is not only for detection with much filtering, but to extract the parameters. Because I told you that the waveforms are not much modified by whatever they encounter once they are emitted. So all the information is actually in the waveform. So for example, from the frequency evolution, we can extract the masses. From the amplitude and the masses, we can reconstruct the distance, where the source was with respect to the Earth. If we can record the waveform in, for example, 3 detectors, the Virgo and the 2 LIGO, we can determine the localization in the place in the sky where the source was. Then, as I was saying before, if you see actually modulations in the phase and in the amplitude as shown in this waveform here, you can know whether the system was moving on an eccentric orbit instead of circular. This is circular orbit. Or whether the spins were aligned with the orbital angular momentum perpendicular to the orbital plane, or if they were precessing. Finally, now that we have many waveforms in general relativity, some groups have started also to build waveform in theory, so-called alternative to general relativity. And so one can do also this kind of test to understand if gravity, if general relativity is the theory of gravity in the strong field and high velocity regime. Okay, so we have to solve this problem, this two-body problem, it's called. And of course, everybody here knows about the solution in Newtonian gravity. We learned it in high school, I think, and of course in our classical mechanics course. Students here may know very well. So I wrote here the solution in Newtonian gravity for the planet going around the sun, and you can also draw actually a line and a curve that represents it. Unfortunately, in general relativity, there is no closed form solution for the orbit. And it's very complicated because the theory is nonlinear. So this ellipse we learn about in Newtonian gravity, in general relativity precess, right? You might have heard about the precession of Mercury, which was one of the prediction of general relativity. Not only, but also this orbit precess, but also it shrinks, right, over time because of the emission of gravitational waves. So we cannot actually have a closed form solution, but we can have approximate solution that we can determine perturbatively. We can also solve this equation numerically. So we have to put together these two groups of people working in analytical relativity, doing paper and pencil calculation, like, for example, Luc Blanchet here in the audience, and people doing supercomputers, using supercomputers, where basically we solve the Einstein equation on supercomputers. Now, why we cannot solve this problem only with supercomputers? Because to produce a simulation of two black holes going around each other for only 15, 20 orbits, which is not a very long waveform, it's much shorter to what we need for our template banks, it takes, I wrote here 1 month. 1 month is only when you have non-spins and mass ratio close to 1, but it can take even a year, depending on how much is the difference between the masses of the black holes in the binary and the spins. So I'm showing you here a simulation, numerical relativity simulation. You see in the bottom the plus and close polarizations of the gravitational waves, and in the main part is the flux of radiation. For an equal mass non-spinning binary, you see these blobs coming out. Actually, the radiation is everywhere, but in particular perpendicular to the orbital plane of the binary. And what is shown there was the flux of radiation in unit of the flux in electromagnetic radiation of the sun, the 10 to 23, and the color was telling you as you were going toward yellow means that the radiation was becoming stronger and stronger. Okay, so let's go a little bit to another level. So how do we solve then this problem? So I introduce here a cube that represents the different methods that have been proposed to solve this problem. Starting from the red one, numerical relativity, this axis represents the mass ratio in the binary, the separation between the two objects, and here the amount of eccentricity going up to scattering. So numerical relativity solved this problem, as I was telling you, but in a restricted region because of computational time. The oldest method is post-Newtonian theory, where you solve the Einstein equation and then also everything basically in an expansion in V over C, and also Gm over RC squared, where R is the separation between the two objects. The two things are intertwined because of the Weier's theorem. And post-Newtonian is very good when the two bodies are very far from each other and then start to lose accuracy as the two bodies go toward merger. You can expand the Einstein equation in powers of G, or Gm over RC squared, so it means weak field still, but not slow motion like in post-Newtonian. You can basically, you don't expand in the velocity, so it can describe also fast motion. And this has attracted quite a lot of interest in the last 5-6 years from people coming from effective field theory, scattering amplitude, etc. I will have a slide later on about that. You can also solve the Einstein equation in another perturbative expansion, which is the expansion in the mass ratio. So here you don't expand in G, you don't expand in the velocity, so it's strong field, but it's restricted to the case in which you have a mass ratio which is really very, very small. So a small body going around a very large body. Now, besides these building blocks, which are fundamental, very important, we also have to do something to put them together and build a waveform that include also the merger and the ring down. So one approach is the effective one-body approach that was introduced in 1999 by Thibaut Damour and myself. And this approach puts together the different approaches and also provides a physical answer for the merger ring down, which is then calibrated to numerical relativity, as you will see in a moment. And this method has been developed over the years with two families, this SUBNR and TOB-RISAMS. No important to pay attention to these names. It's just that sometimes they will appear in some plots later, just to tell you there are different flavors. So these waveforms are built in time domain. We can also build waveforms that are called phenomenological. They are built in frequency domain by putting together effective one-body, post-Newtonian, numerical relativity. And the advantage of this waveform, which are called inspire mergering down phenomenological, is that they are in closed form because you do some approximation in frequency domain, so you can generate them very, very fastly. It's not like producing the waveform in time domain, solving some equations, but they are less approximate, more approximate than, or accurate than the previous one, because you have to do some approximation in order to put this expression in closed form. And these plots here represent the amplitude of the wave and the derivative of the phase of the waveform for a particular value of the parameter of the binary as a function of the frequency, just to show you that it's a quite smooth function. Finally, there is another method that has been developed in the last few years because people are building more and more numerical relativity waveforms. In the region in which we have numerical relativity waveform, also the length, considering the length of the waveform, we can build surrogate, so interpolation directly of the numerical relativity waveforms. And this is an example in brown of a quite complicated with the precession of the spin waveform contrasted with the numerical relativity waveform itself, and also one waveform from an effective one-body family that was not calibrated to numerical relativity. So this is just to tell you that we have this example, and it's very important to have these examples because when we do the analysis, we use more than one waveform model to be sure that what we are actually inferring, the parameters, etc., are correct, that we don't see a lot of differences between different models. Okay, so now I go to the question that was asked before. So until now, all the calculations have been done mainly actually for quasi-circular orbit and in vacuum. Now I put environmental effects in green here, so I put some green around the binary just to say that we have to start caring about the fact that if you have the binary small black hole around the big black hole, the very big black hole can be not in vacuum but can have an accretion disk around, what I was saying before. You could also have that the binary, the black hole is actually maybe moving in some medium. People have been describing maybe effect due to dark matter, etc. Another important thing I mentioned before, that calculation has some of the methods that are used to do this calculation use Feynman diagrams. So if you want to go, for example, if you want to include the environmental effects due to some scalar field, or maybe you go beyond GR and you have new operators, then you have to start including new operators in this Feynman diagram. And people have been using these tools to compute actually waveform in this alternative theory of GR or even with environmental effects. Okay? But of course, we expect that these effects, including beyond GR, are quite small. So maybe we have to check this, but it's likely that in particular environmental effect will be important in the future. Okay, so now are there any questions? Yes.
I have more of a sort of trying to check and understand question. So you're discussing the timescales you show on the x-axis of these waveforms as seconds, right? So you're only
Oh, here there is no time actually. Sorry.
The previous ones.
Maybe. You will see some with some time, but I don't have the time here.
So the detector is only catching the last few seconds of the two black holes smashing against each other?
Yeah. So
this is over a lifetime of billions of years.
Yeah.
And finding two black holes close to each other is much rarer than finding one. So this just sounds like there are very, very, very few scenarios of catching the last few seconds of two black holes smashing into each other.
So, okay, I don't know if I understood one thing that you said. We cannot, so if you have just one black hole, in the solution, for example, of a rotating black hole by Kerr that is rotating, rotating black hole, it doesn't emit gravitational waves. So you need to have two black holes going around each other for having a quadrupole moment that changes as a function of time to produce gravitational waves. Now, I think, okay?
Yes.
Okay, so now what you are saying is correct. We are just seeing the last few seconds, or maybe a minute, depending on the mass of the system, or even a fraction of a second, of a binary that lived for tens of millions of years from the moment in which originally formed. Okay, that depends also how it formed, if it formed in globular clusters, or it formed in some other ways, you know, how much the life of the binary. Because, but this is, yes, this is exactly what is happening. Yes?
So you said that on Earth we're limited by the 1 Hz frequency detection limit? You said something like that.
Well, what I was saying is that, well, that was the frequency of the pendulum. I was referring to the fact that, you know, this plot here, I don't know how well you can see, it's very small, is the noise spectral density of the detector in units of the inverse of the square root of hertz as a function of the frequency. And this is 20 hertz. This was actually the noise spectral density at the time of the first detection. And you can see this rise of the noise spectral density at low frequency, and you see also this rise here. This is due to the shot noise, and this is due to the seismic noise. So you have some sensitivity of a few hertz, at few hertz, but it's very bad, the sensitivity, because our signal...
The seismic noise, because then you said that
Yeah, this is the seismic noise.
space to go beyond the Hertz?
Yes.
Because we get rid of
Yes, exactly, because you have seismic noise here that prevents you to detect systems below 1 Hertz. Actually, we will see later, the detectors like Einstein Telescope, Cosmic Explorer really try to go up to 1 Hertz because this is 20 Hertz, so this is actually not very good, the sensitivity already at 20 Hertz. But it's the seismic noise that, and the gravity gradient noise, which is also another noise that prevents to go actually to very low frequencies on the Earth.
sort of in line with the previous question, so in space there are no other kinds of noise?
Yes, in space, of course, you don't have, I mean, you don't have the seismic noise, but you have other kind of noise. You have the shot noise. You have, you know, lasers that send light between satellite, and you have to care about the fact that, you know, the satellite, inside the satellite you have a proof mass, and this mass also is subjected to noise, and you have to make sure that the satellite moves in a way that the mass is free falling and not, you know, being perturbed. So there are other kind of noise. There's always noise, unfortunately. We cannot do without noise. The important thing is overcoming the noise, okay? But you will hear a little bit more later if I arrive there. Okay, let me actually skip these 2 slides. I want to go to, you can ask me more about the effective one-body. I was not planning to have some more detailed discussion about that. So we have this way of putting together, you know, the different approaches, but then we have to calibrate to numerical relativity, because numerical relativity gives us the best result for the merger, right? We have to use it. So I have just one slide to show you how we do that. So in this upper panel, you have an effective one-body waveform which has the in-spiral, the merger ring down. The ring down is once the 2 black holes merge, a new black hole forms, and the black hole rings space-time like a bell, as is on quasi-normal modes. And that's why you see this damping, okay, at the end. Now, you see that there is some dephasing because the effective one-body is an approximation, okay, of the Einstein equations. So how do we improve it? We add some correction, for example, post-Newtonian correction at an order which is unknown today, and we calibrate it to numerical relativity so that we basically reduce the difference as much as possible. We do also other kind of calibration that will be a little bit complicated to explain here, but what we want to make sure is that at the end the model agrees very well with numerical relativity. And this operation is repeated for many numerical relativity waveforms at our disposal. So this plot here shows for the ongoing run, we built an updated version of our family effective one-body numerical relativity waveforms. We use 441 numerical relativity waveforms from the Simulating Extreme Space-Time collaboration. This plot shows with different colors the different mass ratio of the binary black holes. And this axis here is the combination of the spin in the binary. So for each of these points, we repeat this procedure so that we have very good agreement. And then once we have the best fit values, then we interpolate, depending on the mass ratio, no? We do fits so that we can produce waveform everywhere else in the parameter space. Because in building the template bank, we have to produce waveform for any mass ratio, for any spin, not just for the points for which we have numerical relativity. So in fact, this plot shows you the projection of the template bank in the mass plane M1, M2, used by the LIGO-MIGO collaboration. There are other two axes that represent the spins, but it's not in this plot. So for binary neutron stars that merge in the kilohertz, as I was telling you before, we don't need to add a merger. We just need the in-spiral, and we have very accurate post-Newtonian templates, so we use them for the template bank of the order of 75,000. For neutron star black hole and black hole, for which the merger is important, we have to do all this procedure, analytical, numerical, put them together, and so that we can cover this part of the parameter space. Then for follow-up analysis, to extract the parameters, we also use the other waveform model that I mentioned at the beginning, the IMR phenom, the TOB RISA-MES, and R surrogate. Okay, let me show you some results. So the first event that I wanted to highlight was discovered, as I told you at the beginning, the 14th of August 2019. This was an interesting event because there is a lot of asymmetry in the masses. One is 23 times the mass of the Sun, and the other is around 2.6. And for what people know from nuclear physics and neutron stars, it's very difficult to have a neutron star with a mass larger than 2.2, 2.3 solar masses. So this might not be a neutron star. But actually, it's also very difficult to form a black hole from the collapse of a star with such a little mass. So we don't know actually what is this object. And this is not the only object that has been found with this mass, a little bit peculiar. But let's also observe the mass ratio, right? The mass ratio is 10. Well, the more asymmetry you have in a binary, the more complexity has the signal. The quadrupole is just the leading order of a series of multiples, that determine the gravitational waves. So in this animation here, you see the total signal for this event decomposed in multiples, okay? The polarization decomposed in multiples. And these multiples become, or higher harmonics, become more and more important as you go toward merger, because the amplitude depends on the velocity, and the velocity becomes larger and larger as you approach merger. Now, as this, this is the merger of the black hole with neutron star. So I wanted to highlight here that, for example, if you want to extract with Bayesian analysis the mass of the smaller object, and get with an accuracy of 10% that the mass was 2.6, you had to include in the waveform models the presence of these harmonics and the precession of the spins. If you don't do that, the posterior distribution are much wider. So you see these physical effects do matter if you have a system which has asymmetry. Okay? You would not get correctly the parameters. Now, the other event I wanted to show you is this very massive binary black hole detected the 21st of May 2019. This is a numerical relativity simulation that we did in our department. And here you see the two black holes merging with each other. The masses are so large that the event lasted only really a fraction of a second. And you see here the masses of the two objects. Now, theoretical astrophysicists tell us that you cannot form a black hole with a mass between 60 and 120 solar masses from a collapse of a star because of a phenomenon that is called pair instability supernova. So basically what happened is that the star is collapsing and at some point, if the mass in a certain range, you produce so the gamma decay in E plus, E minus. And at some point, this process becomes basically a reaction that leads, so you produce, E plus and E minus, and what happens is that you don't have any more the pressure, the photon pressure that counterbalance the attraction force of the gravitational field. And so what happens is that the star just collapses, leaving no remnant. And so you should not form these black holes with these masses. So where does black hole come from? Now, if you talk with people working on primordial black holes, they might tell you these are primordial black holes, right? Because you cannot form in other ways. Primordial black holes, I didn't say, are black holes that people think had formed from fluctuations in the early universe, due to inflation, etc., during the period of inflation. So they don't form from the collapse of stars. That's why we don't call astrophysical black holes. Other people suggest that maybe these large black holes may form they were formed from a previous merger of two black holes. So you had the two black holes merging with each other. They form a black hole with a large mass. Then this black hole met with another black hole and form a binary. And this is the binary we are seeing. So these are called second generation black holes. Now, from the point of view of the waveforms, this is the event where the different waveform models gave more differences. So this is the reconstruction of the masses of the two events, of the event, with the three waveform model, SUBNR, phenomenological, and R surrogate, and this is the reconstruction of the spins of the two objects. You see these differences that you didn't see in the plot before, and these differences are not crucial in the sense within 90% they agree with each other, but now if we improve the sensitivity of the detector, these 90% are going to shrink, right? Because they depend inversely on the signal-to-noise ratio. If you don't improve the waveforms, the systematics can dominate, right? The statistical error. That's why we have to improve them. Okay. Now, do you have any question? Because I'm going to say something about neutron star wind matter.
So you can still use the quadrupolar scheme for this?
No, for this one, it's very, thank you, actually, for this one, we need to add the higher harmonics. Because the signal is dominated by the merger. We are seeing basically the merger and the ring down, and there the multiple moments are very important. So it was very important to have them in the waveforms, actually. Other questions? Okay, so let me say something about the neutron stars. So the neutron stars are also beautiful systems. So they have a mass between 1 and 2 solar masses. So the mass is smaller than the black hole from the collapse of stars. The radius is between 9 and 13 kilometers. And why they are interesting? Because we don't know. Of course, they are made by many neutrons. But actually, when you go in the center of the neutron star, you don't have any more neutrons, right? You have just quarks, perhaps. You have maybe strange quarks, hyperons. You can have some phase transitions. And we don't know because the density is so high that we cannot reproduce this kind of physics in the lab on the Earth. Now, why you can say something with gravitational waves? Well, there is a parameter which is different from 0 for neutron star and is 0 for black hole, which is called the tidal deformability parameter. It is basically the ratio between the quadrupole moment the neutron star acquires because of the external tidal field of the companion. And this has an imprint on the waveforms. So here I'm showing in black a binary black hole waveform with the same masses, a binary neutron star waveform. And now you can see that, of course, the waveforms are the same if the two bodies are very far from each other, because you don't care if it is a neutron star or a black hole, right? The tidal effects are very small when they are very far from each other. But as they approach each other, you see this dephasing one from the other. And so by measuring this difference in phase, you can basically learn about the lambda. Okay? And also notice that the neutron star merger is also very different from the neutron star, the merger of two black holes. But today we are not very sensitive to the merger because the noise spectral density of the detector is not very good at merger in the kilohertz. So we are looking mainly in this part here, the in spiral. And I have just one plot to show you that by using GW170817, some bounds at the level of 50 credible intervals and 90 credible intervals have been put on the pressure and the density that you can see in this plot here. And also the radius of the neutron star has been constrained at this level, okay, 11, 12 kilometers with an error which is not negligible, but is quite interesting. And this measurement can improve as we have more neutron stars. Unfortunately, we are not detecting many neutron stars. But in the future, this can be improved, these kind of bounds. Now, of course, you might wonder, okay, did you see a mixed binary? Yes. The 15th of January 2020, the first neutron star black hole was observed. This is actually a simulation done by Tim Dietrich in Potsdam. And you see here the neutron star black hole going around each other, and now the neutron star being swallowed completely by the black hole. Because of the choice of the masses and the spins, there is basically no remnant, no disk remains there. If you had a disk, which can happen for different choice of the parameters, then you could have an electromagnetic counterpart in this case. Now, to put it in context, this is the posterior distribution of the masses of the event in blue here that I'm showing you. Now, the only way in which we can say that there was a neutron star in this system is because the mass is in the range between 1 and 2 solar masses. We couldn't measure any tidal deformability for this event because the tidal deformability becomes is suppressed when the mass ratio increases, and a neutron star black hole has a larger mass ratio than a binary neutron star, where the mass ratio is close to 1. Now, I wanted to mention the only event of the latest run, which was published last April. This is a neutron star black hole again. You see here the simulation. And now what is interesting of this system is the mass of the black hole. Well, we think it's a black hole, has a 3.6 times the mass of the sun. The other object is a neutron star. But again, this now poses some challenges because we have not seen black holes so small until now from the collapse of stars. Even in our galaxy, I told you at the beginning, the red spots in the plot where the black holes in X-ray binaries in our galaxy, they typically are not in this mass range. This is called the low mass range. And so this is also posing some questions. Are they really black holes from the collapse of stars? Or maybe, of course, people also have been advocating that these could be primordial black holes. It's very difficult to think of them as very massive neutron stars on the other hand. Okay, let me skip this. I want to start discussing some tests of general relativity, but wow. I was checking my time, and I have many slides. I have many questions. So do you have any question, by the way, before I start talking about tests of general relativity? I continue. You have to stop me. No, sorry, Hilton, yes. How much time I have? Oh, 10 minutes, okay. I can skip some parts, no problem. I had already several questions. Okay, so I want to talk about, let me check the time then, two tests. Okay, so the first one, so we do tests of general relativity in our solar system, right, and also in cosmology. So here we are testing in a different regime because we have two black holes, merging with each other. The space-time is dynamical. The body moves at the speed of light. So I wanted to mention this test of the quasi-normal modes. So I told you before that when a black hole is perturbed, it emits quasi-normal mode. This was found in the 70s. And now this happens when the two black holes merge with each other. Again, another simulation of the very first event. So this is this very powerful last part of the radiation. In the same way as spectral lines in electromagnetism can identify the chemical elements, whether it's hydrogen, neon, beryllium, etc., it turns out in general relativity, the quasi-normal mode frequency only depends on the masses and the spin of the black hole. So if you can measure these quasi-normal modes, you can do tests to understand are they consistent in general relativity or they may violate general relativity. So one of the flagship tests of general relativity of the ring down done by the collaboration was developed in our group where basically you assume that the quasi-normal mode frequency are the one of GR, okay, and the decay time and the real and imaginary part of the quasi-normal mode, but then you add a small deviation. And what you want to do is that you want to do a Bayesian analysis where now you have these two new parameters together with all the rest. By the way, waveform depend on 15 parameters for binary black holes when you add all the effects, also including the distance, the location in the sky, etc. So you add these two parameters, and how these parameters change the waveform. I have a little animation, so if you change the frequency, you can see, how much the waveform changes and the frequency is changing. If you change the decay time, then you can see how the amplitude is changing while the frequency remains the same. So this test was done with the events of LIGO and Virgo, and this plot shows you the deviation from the fundamental mode, which is the quadruple mode, delta omega and delta tau. General relativity is here, 0. And you can see, okay, all the events, but in particular highlighted the two events that have the larger signal-to-noise ratio in the ring down. So general relativity is not violated. We are basically measuring this quasi-normal mode, the fundamental one. But until now, not more than the fundamental mode, just one of them. There is also another method that is used by the collaboration to do this test of the ring down, which use just dumb sinusoid. But the results are, general relativity passed the test. So the other example I wanted to give is a test similar, but of course has these differences, from the so-called parameterized post-Newtonian test in our solar system, but now applied to the phase of the waveform. So if you write the phase of the waveform in a frequency domain, you have an expansion in Pn, in post-Newtonian, in V, okay, V to the power n. And this coefficient, again, in red, are the prediction from GR. They depend on the mass of the system, the spins, and then you can add deviation. And now you do the same thing I was explaining before. You allow this delta phi hat to change when you do the Bayesian analysis, and you find that the posterior distribution, after marginalizing on all the parameters of these parameters here, delta phi hat, encompass 0, so GR is not violated. And then you can use that to put a bound on these post-Newtonian parameters. And this is what this plot is showing you here. For the different post-Newtonian parameters, you can have the different events, but also combining the events, you get the best bound. For 0 leading order Pn, 0.5 Pn, 1 Pn, I wanted to draw your attention on this minus 1 Pn. What is that? Well, if the theory of gravity is not general relativity, but is a scalar tensor theory, you have actually also dipole emission. The leading order term multiple is not the quadruple, but the dipole. And the dipole emission is particularly important at low frequency where you have the longing spiral. So in particular in the longing spiral. And so this bound, the best bound, not surprisingly, is set by the binary neutron star, almost 10 to the minus 5. And the neutron star black hole I was just showing you before from the latest run is the first bound on a system with a black hole. Because there are some theory alternative to general relativity, like Scala-Gauss-Bonnet, for example, for people here familiar with that, that predicts a scalarization of the black holes, not just a scalarization, I mean, in that case, not of neutron star, but black holes. Okay, any question about the test of GR? There are many more, but I just focus on these two. No questions? Okay, let's move forward. So I wanted now to go, since I think I might have 5 minutes. Yeah, so I will skip some parts, but I want to tell you what's going to happen, okay? So, so first of all, this is actually what happened in the last years for the different observing runs. We are at the fourth observing run. This number is at which distance in megaparsec we can see a binary neutron star. So the increase of this number means the detectors are becoming more and more sensitive. So this run will end sometime in October. There will be a gap to improve the interferometers, and we'll come back online at the end of 2027 with a 5th run. There will be some upgrades of LIGO and Virgo in early 2030, but these detectors are going to be still looking in our local universe at a redshift of 1 or 2. Now, I'm going to skip this eccentricity, so you can ask me. So let's discuss what happened then after the beginning of the next decade. So we expect, but this is not yet funded, new facilities on the ground, the Einstein telescope in Europe, and Cosmic Explorer in the US. And now you can see the noise spectral density of the current detector, Advanced LIGO, contrasted with the one of Einstein telescope and Cosmic Explorer. You can see now that these detectors are trying to go at low frequency, up to these few hertz I was mentioning before. But also the improvement is 1 or 2 order of magnitude, which means, a factor 10 in sensitivity means a factor 1,000 in volume, right? So it means that you are sensitive to a patch of the universe 1,000 larger, so the number of events will be much bigger, and also you can go at much larger redshift. And in fact, these detectors will bring black holes of larger mass, because going to few hertz means you can see black hole of 1,000 solar masses, not 100. And you can go at a very large redshift at the epoch where the first stars formed. Now, it's quite amazing to think at the number of events we will see with this detector. The strongest one, with a signal-to-noise ratio larger than 100, we will see of the order of 10,000 of events in a year. Okay? And almost 500 binary neutron star in a year with such a large signal-to-noise ratio that we will be able to nail down really the equational state of neutron stars. Now, because we have larger black holes, the signals are going to be also more complicated because now you can have, sorry, I don't know why my computer also is getting tired. I don't know why I cannot go to that plot. Okay, so you can have a small object around a large object of 1,000 solar masses, so the signal can be quite complicated, eccentric, etc. This is the snapshot at 1 Hz and 10 Hz. Then there is the beautiful mission LISA. So LISA has been adopted as a mission by ESA, which means it's under construction, so by NASA, just last January in 2024, and the launch is predicted for 2035. It seems a long time from now. It's not a long time. Many things have to be prepared. So as you can see, it's a triangle configuration going around the sun just behind the Earth, using still laser interferometry. And this plot shows the noise spectral density of LISA, which is now focusing in the millihertz, and several signals here. So what are they? Are the million solar mass black holes at the center of galaxies that at some point form a binary system, and then they merge with each other. And these tracks represent the merger that one can see for weeks, for months, not just a fraction of a second or a minute. There will be actually sources like the stellar origin black hole we are seeing today, which start to sweep in band in LISA, and then after a few months, a year, they can be discovered by the detectors on the ground, because the frequency moves. And all this gray region here are all the white dwarf, many white dwarf in our galaxy, white dwarf binaries. They also emit gravitational waves in the millihertz, not in the bandwidth of LIGO. So the sources are very complementary, including this, now I put again this plot. These are the extreme mass ratio in spirals. So you have a very small black hole going around a very large black hole for millions of cycles for an entire year. And for that, we need to build the waveforms, actually. So the problem is complicated. I skipped this. So we need actually to advance the theoretical predictions and get waveforms that are more accurate by 2 orders of magnitude with respect to what we have today. This is what people have investigated and found. This is the expectation. This object can be an accretion disk, I was saying before. They could be perturbed by a third body. So the binary could be somewhere, but then there is a third body that actually has an impact on the dynamics and the waveforms. I mentioned to you we have to start caring about gravitational lensing. You have a binary emitting gravitational waves. It propagates, it passes through a galaxy, and then is detected by LISA. the signal is going to be modified. In black, you have the lens signal. Depending on the magnitude, the mass of the lens, you can see in color how the waveform is modified, having even kind of echoes, or this would be the multiple images that we see in electromagnetic astronomy, right? Today we see multiple images. In the case of gravitational waves, we see multiple signals coming at different time, but coming from the same source due to the lens of, which is in the middle. So we need to improve this perturbative calculation at higher order. There have been a lot of work. I don't know if there are people here working in scattering amplitude or effective field theory, but in the last 5 years there have been a lot of papers. People are pushing this calculation as an expansion of G at higher orders. We had also progress in traditional post-Newtonian methods, thanks in particular to Luc Blanchet and this group that recently, last year, had the 4.5 post-Newtonian order completed. Okay, something is telling me I have to finish. Yeah, I don't know what's happening. But just the last slide. So the frontier is to achieve 5 post-Newtonian. So in this table, if you go in this direction, you add powers in G, post-Minkowskian. If you go diagonal, because the expansion in V is intertwined with the expansion in G, you have post-Newtonian. So the frontier is 5 p.m. and and also 6 p.m. We are not yet even at 4 p.m. completed, but this is what we would like to have. And this is a beautiful video of the extreme mass ratio in spiral, this million of cycles that we want to have ready for LISA, because by monitoring and probing the space-time around the black hole for so many orbits, we can really test general relativity in an exquisite way. So this is very important. So let me skip this, summing up. So solving the relativity two-body problem has been complicated, but successful so far. The last 20 years have seen tremendous progress, thanks in particular to this synergistic work at the interface between analytic and numerical relativity. This plot shows you really, where are we going in time. The cumulative number of detection with SNR larger than 10 with a different observation run, the beginning of the next decade, Einstein telescope, Cosmic Explorer, LISA, these numbers are really overwhelming. The signal-to-noise ratio of the first event, if we would detect it today, would be, not today, here, would be almost up to 100. It had a signal-to-noise ratio of 23. Okay? This shows how the detector became more sensitive. And that binary black hole would be detected with much higher signal-to-noise ratio in the future. So we need to have this improvement by a factor 100 if we don't want to misinterpret the results. Although I didn't show you one example in which we show that that's the case, but you can ask me as a question. And there are many opportunities for theoretical physicists to contribute. Maybe some of you will join the effort. I want to thank my department. A lot of work I showed is based on their work, and also the experiments, the collaborations, and the agencies. Thank you very much for your attention. And sorry for taking more time. Yes? Sorry, can I ask?
Yeah, there have been many questions, and I certainly have more.
So just could you say something about squeezing? Does it actually help in practice?
Squeezing light.
Yes,
yes, absolutely. In fact, now I don't have a plot here, but so in the current run, 04, for the first time, LIGO and then Virgo used frequency-dependent squeezing. So they built cavities of, if I remember correctly, it's around 40 meters outside the main facility of the interferometers to basically produce a squeezing which is not constant, but depends on the frequency. And this allowed basically to shape the squeezing in a way that you can take more advantage of it. And in fact, I think the level of squeezing that is used today, it's around 10 dB. And this will be even more important for the next runs, et cetera, in the next detectors. So it's very important.
mentioned that gravitational waves can just pass undisturbed through, galactic distances. So what's the basic difference between, Maxwell's equations and Einstein's equations, which make gravitational waves pass undisturbed, whereas electromagnetic waves get scattered or absorbed?
Yeah, well, so they are actually affected. As I was saying, for example, the gravitational lensing, which is affecting the electromagnetic, waves, and we see these multiple images, in electromagnetic astronomy. So they also are there. For example, phenomena like diffraction, if the gravitational wavelength is of the order of the lens size. But these effects are just very small, much smaller. I think it's also a consequence, I believe, of the force of gravity being much smaller than the electromagnetic force. So this effect will be important because if you don't include them in the future, with the sensitivity that will become much better, we could confuse the presence of this effect with maybe the masses being different, because these parameters correlate, and we could get the wrong masses, the wrong spin, if we don't include all these effects. But they are important at some level. Luke, yeah.
In your first slide showing the black hole masses, there is also the black hole that has been discovered by Gaia recently in our galaxy, and which has a mass of order 33 solar masses, much larger than the average solar mass. And this is very nice because it explains better naturally, I would say, the distribution of large masses.
Yes, that's quite interesting. It's not in that plot. That plot is done, if I remember correctly, that plot does not include that event because it was done before the discovery of Gaia. And I don't think people have included. Maybe I should tell them to, because it's a plot done by people in the collaboration. Okay. Yeah, because what Luke is also pointed out is that, so this black hole we are seeing have a mass which seems not to be consistent or much larger than what we see in our galaxy. But this black hole of Gaia somewhat, overlaps with some of the events we are seeing. Okay, other questions? Can you increase your voice, sorry? First generation. Okay, so in reality, I would say we don't know, because the only thing we know at the end, we extract the masses, right? So if the masses are such that the black hole could form from the collapse of a star, then the first thing you think about is, okay, this is a black hole that comes from the collapse of a star. You don't need to talk about second generation, right? Now, for what I know, so people working in trying to understand how binary black hole form, they point out that once two black holes merge with each other, you form a black hole at the end, the black hole can get a kick or recoil, right? Just for the conservation of the linear momentum. And so this black hole may end up going a bit outside of the galaxy, and if they do that, it's less probable that they will encounter another black hole to form another binary. So it's true that you can, use the second generation channel, but it's not considered the main way, the main channel to produce this binary system. So it could be a subpopulation. You might see some of these events coming from second generation, but it cannot be the totality, because it's unlikely that each time the black hole will see another black hole and then form, a binary system. But as I said, at the end, we measure the masses. It's difficult to reconstruct what happened before.
All right. There have been many questions. I'd like to thank you again, the speaker, for answering.
Okay, thank you.